Right, I think now we can start. It's already 8 minutes past the given time. Uh, cool. So today we'll be starting off with DP. So for making you understand what exactly DP is, and we'll uh, start with this particular question, minimizing coins. So today's target will start with a recursive solution for this question, and then we'll see how we can reduce the time complexity and why exactly DP is even required when somehow it is based on recursion only. Uh, right. So we'll first of all write a solution based on recursion, then we'll see what memorization is, and then we'll write the same solution using top to bottom approach, and then we'll improve on that. Okay. uh, so first of all, what does the problem statement say? We'll discuss the problem statement. So we are given a particular number x, and we are given a few coins. We are given n coins. So for this particular case, the coins are coins of 1, coins of 5, and coins of 7, and we are required to use the minimum number of coins to reach to the particular sum value, which is x. So for the in the example case, they have given 137, and we have to reach to 11. So if you want to okay, they have given 157. Yeah. So we'll just change it 5. Yeah. So if the the best case in which we will require the minimum, which we can think, is 5, 5, and 1. It will only require us using 3 coins. So the answer will be 3. Right. So how do we approach using basic recursion? Think in terms of recursion. Anyone has any ideas? They can the unmute themselves and share the ideas. First, I want to listen to if you guys have any ideas. Uh, anyone? Guys, like, keep the in, do interact. If you guys share the ideas, not necessary it's correct, but you should definitely give it a try. Just basic recursion based idea, nothing, no optimization, just the brute force approach. uh, and if you have any doubts, like, stop me right there, and you can just ask your doubts. You can unmute yourself and ask your doubts. Fine. I'll take you to the idea. So what we can do, either we have two choices. We can subtract 1 from 11, or we can not subtract 1. So for each particular number, we can either use it in our summation to get to the next value. So for example, uh, if we have, I think I can increase the size of text if it's okay. Yeah, I think now it will be more visible. So first of all, if we have 11, we can either choose 7 in our solution or not. So if we choose 7, it will become 11 minus 7, and we'll reach a number 4. So now our next question will become, with 4 and we have these three numbers, or and if we don't choose 7, we'll have another case where we have still 11 and we have not chosen 7. So now we'll start from 5 again. uh, Once I code, things will become more clear. So if we try to start writing a solution, so uh, if we'll have the basic libraries, then we'll make a main function. Then okay, so we'll look at the format. So we are given two integers, and the first one is the number of the elements in the vector which contains all the coins. We can use, so the first one is n, and then we can take x, we okay. So I'm using vectors here. So vectors is basically nothing but it's just like array. It's just more optimized, and you can apply more functions here. So if you are unfamiliar with vectors, you can refer STL in C++. You can note it down. So we initialize a vector v, and while n minus minus, we push the elements whatever we have, we'll be taking in. So we'll have a temp, we'll take in n first, then we have to take in x, then we initialize the vector, we take in the value which is given, and we push it to our vector. So we have to push back temp. So at this point we got our vector. Now we'll make a function, and we'll push these informations to the recursive function. So we'll keep it int type cmin. So first of all, we'll take in the vector, and then we can take another integer which is the sum, and we can take another integer which will basically tell us till which index we have reached. So let us call it I, and now we can just call the function. Guys, if you have any doubts anywhere, any point, please unmute and ask. Right, don't hesitate to ask any doubt if you have any problem, and if like I do any mistake, you can point out the mistake also, right? Okay. See out cmin. So first of all, we are passing the vector, then we are passing the sum value which is x, and then we are passing I is the size of the vector. So you can get the size of the vector directly by v dot size. So yeah, right. I hope this is visible. If I can increase the size, might be better. Okay. So this is just the input part. Now we have to start writing the recursive solution. So recursion always has two parts. First you have to think of the base case, and then you can write the recursive part. So for thinking for the base case, you simply have to think about what will be the smallest possible input. So here we have s and here we have I. So the the size of the vector can be 0, or the sum can be 0. So two things we can directly come up with. So if the sum is 0 at any point when we come to it, then we should, then if the sum is 0, the minimum number of coins will be 0. So we can simply return 0 in that case. Or if I is 0, so you should understand we are not taking the index. Since we have we have given the size, the index will be I minus 1, it won't be I. So that's why it's 0. It's not the index, it's index plus 1. So if this is 0, then we don't have any solution. So think about it. If we have any values of sum, if it was 0, we have will already return 0. If it's non-zero, so if we are coming to this point, means the sum value is not 0, and I value, you don't have anything in the vector to use. So means you're not able to solve it, means there is no possible solution. So you have to return -1. So if there is no possible solution, you can return -1. Right. So that's all for the base case. Now we have to write the recursive step. So how we'll start is, so just discussed, we had one case in which we are using the particular coin at ith place, and other case in which we are not using the coin for ith case. So we have one case where we are calling cmin, vector is the same. We are not, if you are not using, the sum will remain the same, and the I will just become I minus 1 since we are not using it. And the other case will be cmin, where we are using it, so v will be the same, and it will be s minus v of I minus 1. So we are subtracting from the major value, the total value, we are subtracting the particular number at that index, I minus 1, and then we'll pass back I. Why we are not doing I minus 1 here? Because there is a possibility we might use that particular coin again. So in that case, if we are only using ones, if for getting 11 we are only using ones, so we might use it 11 times. So if we move ahead here, then we won't be able to use the particular same coin again. Okay, so and here so now these are the two cases. Now which of these cases should we actually use? So let us think. So this case will also give us some output, and this case will also give us some output. Since our task is to minimize it, so we will have to take minimum of these two. We have to take the minimum number of coins they return. So since we are using another coin here, since we are subtracting, means we are using one coin here. So we'll after writing the whole code, we'll again do a dry run to understand. So here we have to add one. We are adding one because we are asking it after using one of the coins. So we have to take minimum of these two. So our final answer will be the minimum of this particular function and this particular function. uh, but now, are we missing anything? So uh, if we get a case where it is always possible, this will work. But since we are, if it is not possible at all to get it, then we cannot return this particular number directly, right? So if this particular function returns -1, then it will be a issue. uh, you guys are getting the point. So if we are getting -1 back, means we need to return -1 only to show that there is no possible uh, outcome. This is one thing. And another thing which you should think of here is ki we cannot always subtract. So for example, the sum is given 11 and we have some coin which is of 15 rupees. So now we cannot use this 15 rupee coin uh, to we cannot subtract 15 from 11 to become a negative number, right? So this case also we need to eliminate. So we'll see how we can eliminate. So first of all, we can only use this function. So we'll eliminate the first thing. So if we get v of I -1, if this quantity is greater than s, then we have no other option. We will have to return the quantity where we are not including the coin. So we cannot include the coin at all. So we will in yeah, in this case we will directly return the case where we are not using the coin. So Cmin, we are just reducing I by 1, that we cannot use this coin, right? And so this case will directly eliminate the possibility of getting a negative. Now we have to correct the other part. Other part is if we are getting -1 as the output. So for that, what I'll do is I'll use two variables L and M, and before directly putting the output, I will assign them with the output. So I will assign L with this one, and I will assign M with this one, right? So we will not sum 1, otherwise this will become 0 if it's -1. So now we can simply check if it's -1. So if L is equal to -1, we can simply return M. So since we are returning M, even if M is -1, we'll return -1 only. So we won't have any issues. So we'll return M. And also we can do the same thing for M. So if M is -1, we can return L plus 1 as we discussed. So, and in case these both are not -1, we'll come back here and we can return minimum of L plus 1 and M, right? So I think now the recursive code is done. We have, okay, we'll just run it for a simple example. We okay just have to remove one excess bracket here. Anything else? 34. Min of, okay, here you have 2 years. ln, put a bracket, yeah, right. We will run again. Cool. So we got 3. So that is what was the output we just discussed. So we'll quickly uh, try to do the dry run of this particular code. So what happened is uh, we will, okay, we can increase the size, right. So we had these 3 numbers and we had the sum as 11. So first of all, we asked if we started from 7. Uh, so we checked uh, if 7 is greater than 11. So first of all, we are checking if the number is greater, and yes, okay, so this is not greater, so we'll move ahead, and then we calculate with including. So if we include 7, we will pass in the function subtracting the value 7 from 11, that will be 4. 4 will be the sum, and still size will be 3 only. We might again use 7. So after uh, this again goes, and then this we again check is uh, 7 greater than 4, and yes, it is greater. So we will pass, we'll simply ignore 7, so we'll pass 4 comma 2, and after this goes, it will again check is 5 greater than 4. Yes, it is greater, so it will pass 4 comma 1, and for 4 comma 1, is 1 greater than 4? No, it is not greater than 4, so we'll actually subtract it. So we'll have 3 comma 1, and then we'll have 2 comma 1, and then we'll have 1 comma 1, and then we'll have 0 comma 1, and as soon as we have 0 comma 1, we have our base case triggered. So our base case will return 0, and since every time we are adding 1, we'll get our answer. But this won't be the final answer. So this is one particular answer. So finally we'll get the minimum. After using 7, we'll so with this we'll also have another loop which will skip 7 directly, and I'll, one sec, yeah. Right. So if we can reduce the size, yeah. So which will directly skip 7. So after first of all, we called 11 comma 3, and then after that we are going to straight away leave 7, and we'll call 11 comma 5. After calling this, we'll check if 11 comma 2. So at index 2 minus 1, that is 1, we have 5. So we'll check if 11 is if 5 is greater than 11. So it's not greater than 11, so we'll subtract. So 11 minus 5 will get 6, and then again we'll pass 6 comma 2, and then we'll again subtract 5 since 5 is not greater. Then we'll get 1 comma 2, and then 1 comma 2 will 5 is greater than 1, so we'll get 1 comma 1, and then we'll get 0 comma 1, since 1 will be subtracted. I think this approach is clear. I hope if you have any doubts you can ask. We have just seen the recursive approach. uh, is it clear, guys? uh, Anyone can unmute and answer any doubts, anything. It will be better if, like, if you're not understanding any point, it will be better if you ask, otherwise you'll like just be confused. It's okay to ask any question. uh, Fine. Okay, no doubts. Fine, I'll move ahead and move to the memorization approach. So, what you guys can observe here is, uh, after calling a particular function, we might call that function again. So, uh, since we are, uh, yeah, so we have a, we are calling the function into multiple directions, and then this particular thing is again uh, calling the function. This function is again calling the function. So like this we uh, form a tree. So there are chances that two particular nodes of the tree, so for example this particular node and this particular node might be the same. So when you are trying to compute this particular uh, node, when you have already computed this particular node, if you can store this, if after, for example, somehow I got to 1 comma 1, so after computing 1 comma 1, I got to 1 comma 1 here also, in this one and in this one. So if I store 1 comma 1, I can directly get it. So if in the first case here, when I reach 1 comma 1, I store the value. Then if I come to the same thing again, so I can first check if I have this value stored. If I have that value stored, we can directly return. We won't have to again call the recursion loop, and again it goes to several steps. That part can be saved, right? So will it's very simple to convert a recursive code to memoized code. So uh, we will see what exactly change will okay we'll make changes right to this code, and we'll see what changes are required to memorize a code. So simply what we are doing, we are saving the changes, saving some of the recursion calls, right? So we will initialize a vector of a vector. We will name it dp. So we are initializing the vector here. Then after, so what will the vector actually be? Will be in the vector will be storing, one side we are storing the indices, and the other side we are storing the sum, right? So here you have stored the sum, which is the total, and here you are storing I values, right? So we will resize it, dp dot resize. So these all particular functions you will learn while learning STL. So if you don't know STL for now, try to understand the logic, and you can learn the STL part uh, after the meet or afterwards. So now you have to think of the size. So we'll always will take sum plus 1, and why we are doing that is, so here we'll have x plus 1, and I'll tell you why we are doing that. We'll take x plus 1 here, and here we'll take n plus 1. Okay, so see, uh, we we need the zeroth line, so we won't be, so we'll uh, when the sum is 0 we need it uh, to store 0, because if sum is 0 we are getting 0, so we cannot use the zeroth index of the dp table. So for 11, so if we are going back by -1, we won't get this line, right? So we cannot have -1 here, right? Indexes start from 0. So in zeroth one we are having our base case, right? So that's why we are not starting from 0. Cool. So we have resized our uh, dp, and yeah, vector of vector is basically just two dimensional. You are having a vector where each element is a vector, so you just get a two-dimensional space, uh, just like this table I have drawn here. This is a vector of a vector, so you can consider this whole as a particular vector, and which is storing these vectors: first vector, second vector, third vector. This is stored in a vector, right? uh, so first step was we made the dp table. Secondly, we resized it, right? Okay, and since we have declared it here, it's a global variable, so we can access this dp table now from anywhere. Okay, uh, we resized it, and now what we'll do is, first change in our code is if, okay, so another thing we can do is we can uh, put a default value, like while initializing we can put a random value which is out of our scope, so we can never achieve -2. So we get to know this particular entry is not being used. So here we'll check if dp s and I is is not equal to, if it's initialized it won't be equal to -2, and since it's not equal to -2, we can directly return whatever is contained in this particular space. We can directly return it, right? And if we have not stored it yet, if we have not come across this particular thing before, then what we can simply do is we can assign in our table. So whenever we are uh, returning any value, we can simply put dp of s and I equals to 0. So whenever we are returning it, so okay, so what this particular line does is 0 will be stored in this as well as returned back, right? So wherever we are returning stuff, we can simply put this, so it will just be stored. We are doing nothing but storing this value and then returning it. So here is a return part, here we have a return part, and at the end this is that's all. Okay, so now we have stored the value every time we are returning it, and we are also checking if we have already come across this particular case, we'll directly return, no need to compute it again. We'll run it just to check for this case. We got our answer. So we significantly reduced our time complexity. So for this particular case, if you think the worst case, what exactly we are doing is we will have the time complexity as O of whatever will be the sum into whatever will be the size of the array. But for the recursive case, it will be a lot. It will be exponential, because we are again and again running the loop. So in worst case it will be like 2 to the power n, right? So now see we'll try to see what exactly we did. So this was a for if I can copy this and paste it here. Yeah, so for the memorization approach, we had this particular was the answer. We had to find 11 comma 3, dp of 11 comma 3 we had to find. So we called we checked this one and we checked this one, and we took minimum of these two, right? This was the approach. And for this we did the same. We checked this and this, and we checked this and this, so until and unless we got our base case. So uh, we are going from bottom to top, right? So this was bottom to top approach, right? But now what we'll try to do is we'll uh, come back from top to bottom. So what we'll do is we'll run a loop and we'll start from 1 comma 1. We'll start, okay, we'll initialize this. These uh, will be initialized because we know the answer. If sum is 0, we'll have to return 0, and if sum is non-zero and we have no particular element, we'll have all minus ones here, right? So here we have all minus ones, and in this particular column where the sum is 0, we have all the zeros, right? So now we'll start from this particular column and we'll try to reach our answer. So what we'll do is we have passed it here, we have resized it. Cool. We'll remove this particular code. Yeah, and now we have to run loops to from top to bottom. So whenever you are doing the top to bottom run, there will be two things. First, you have to initialize. So initialize is just like the base case, as we discussed. We have seen the base cases. If the sum is 0, then you have to return 0, and if sum is non-zero and you have no elements left, you have to return -1. So we'll quickly initialize that. So for initializing, we can run a for loop int I if I is less than equal to. So this will be when sum is 0. So when sum is 0, we have to when sum is 0, we have to traverse through this. This is n, right? So when is equal to I here, since I is the size of the array. Okay, actually we don't even need to get I. That was for the recursion, so you can simply emit it. Yeah, so what you can simply use is v dot size here directly, right? So we have to come till v dot size 11, as we have seen, and I plus plus. So now we have to quickly. So the first one is the sum. So the first one is the sum, and the second one is the indices. So sum is 0, and the indices can be I. So yeah, here we have to start from 0. This will be 0. We have already discussed y, and then for the if it's non-zero, if it starts from the sum starts from I, and the sum goes till s, then it will be and there are no elements left, we have to put -1, right? So this particular is enough for initialization. Now we have to run our loops. So uh, for filling the array, will run two loops. So two loops will be enough to fill the whole array. So uh, we'll have we'll just copy this particular part. So only change will be, we have to start from 1, as we discussed. We have to start from 1 comma 1. We have already initialized the zeros, so we have to start from 1 comma 1, and then we'll have the second loop, which will have j right. So now we have so we are starting from 1 comma 1, the loops, and now we have to first of all fill this particular element, and this should be filled with either this or this, but we have uh, seen in recursion that we also have to make sure that the if the element is less, we are directly returning it. So we'll just take care of that. So we will quickly check if, so here I is the sum. So if I is less than v of j minus 1, so we are using -1 since we are traversing from 1 to the size, right? And if this is the case, we can put dp of I j will be equal to it will be equal to dp of, so we are not including the element, so the sum will be as it is, and we'll have j minus 1 passed, right? And this will always be filled, so since we are going from 1, so always we are starting from 1, then we'll go to 2, then we'll go to 3, so always the previous case will be filled. We'll also do a quick dry run to check it. So yeah, or the other case will be else. So yeah, so if it is now we have to check both the cases in which we are taking the element and the other case in which we are not taking the element. So before that, we also need to check if it's a -1. So we'll quickly check that if dp of I minus v of I I minus, yeah, so yeah, v of j minus 1 dp of I minus 1 and j, yeah. So this is the case when we are subtracting the number. If this is equal to -1, we can simply continue. sec. Okay, so this is one case. We'll see what to do. Okay, so the second case uh, will be uh, okay, uh, dp of uh, this case where we are leaving the element. Okay. If this is equal to -1, then we can return the other one as we did in the recursion case, and in the last case we have to will return dp of ij as minimum of 1 plus uh, here we are using the element, and the second case we are skipping the element. So if you compare it with the recursion, it will be pretty similar. So here we'll have dp of I j is equal to the other case, and here we'll have dp of I j as the case we are including the element. We'll put the semicolons wherever required. Right. So yeah. So what we did, we are running two loops from 1 comma 1, and if the element is greater, we are simply ignoring it. If it's not greater, we'll check is it possible for including it, is it possible to leave it, and if it is possible, then we have both the cases. We'll take the minima. We will try to run it. Right, so we have forgotten some brackets. Here it's fine. Here we have to close this bracket, and then this is fine, and here again we forgot to close the bracket, and here again we have to close the bracket. Yeah. Okay, yeah. So finally, what we have to do, we got our array. So we ran the loop, we did everything. So we know this is our answer. So yeah, we forgot to return it, right? So simply after both the loops are over, this is the first loop, this is the second loop, and after the loop is over, you can simply return it. So return dp of the sum was s, and this was v dot size. So this will be the final output which will be returned. Okay, some issue, it is 1 second. We don't need to initialize it with anything in this case because we are not using it, and we'll just quickly check it. The base case, if the sum is 0, uh, if you have any doubts you can again ask. I know it will be like a bit confusing for the first time, uh, but yeah, you guys can ask any doubts. Yeah, so we are initializing when the sum is 0 and the other elements are anything, will return 0. If the sum is starting from 1 and the elements are 0, then we'll return -1. We have the first loop, we have the second loop. Now if it's greater, we have the okay, yeah, got the issue. So here we don't have size. This was for sum, this was for size. So here simply we have to put s, since this loop is running from 1 till s, not from without size. Yeah, we fixed that issue. Now it should okay. Checked if this is greater, we are not including the element ij-1, and otherwise we are checking if the first element is -1, then we can return the second element, and we'll check if the second element, if without including the element it is -1, then we'll return the okay, right, we have not added one, right. So here we added one and here we forgot to add one, so we have to return +1 here. Right, we got our answer. So this was the okay, so now I'll, for understanding purpose, we'll quickly fill this particular table. Okay, so we'll see how this loop is exactly working. We'll quickly fill it. So we first the initialization part. If the sum is 0, 0, we cannot do anything. If the sum is 0, the first two loops are doing this part, right. And if the sum is non-zero and we don't have any elements, then you have to return -1, right. So you have to return -1. Quickly fill it. Yeah, so now for this part we have to calculate we have to get the minimum of this. This is not possible, so if the sum is 1 and we have to subtract 1 from it, so this will have this number of cases here +1, then so 1 comma 1 is filled. Now for 1 comma 2 you cannot subtract, so you just leave the element, and from previous it will be 1 and from previous it will be 1 again. Now for this case, so this is again not possible, and so here you have 1, so you subtract 1 and then use this case, so you will get 2 here, then with 2 you have to take a minimum of uh, these. So in this case you have subtracting 1 and then 1. And for here, since the element is 5, yeah, and you should not get confused, here the uh, element is 1, here the element is 5, here the element is 7, right? So still this case is you cannot subtract uh, 5 from this, so you'll again get 2, and you again get 2, and similarly you get 3 here, you get 3 here, you get 3 here, until unless we come to 5 we'll get the, we have to subtract 1 1 1 1, so you'll have 4 4 4, and now the loop goes here. So with ones you can definitely subtract 1 here, so you will get 5. So you are basically subtracting 1 5 times from this, but now you have 5, so you can just subtract 5 and you can directly get it. And here 7 you cannot subtract, so you'll get the minima, which is 1. Then you come here. So again, if you have only 1 you will have 6 here, so you can 7 here, 8 here, 9. So I'm quickly filling it. We have to do the final part, and then you have 1, and then you can again use, so now it will trigger after you subtract 5 from 6, you'll have 1, so it will go to 1 comma 1, and it has seen it's 1, so it will just add both, so it will add this and it will add 1 comma 1 to give you 2, and this will just do the minima again, because we can still not subtract 7. So this is 7, so again this will subtract 5. Now it will trigger 2 comma 2, so 2 comma 2 is 2, so it will add 2 and the particular solution for 5, so it will return 5 and 2 7, sorry, for it will return 3. So first for subtracting 5 and then 2 times subtracting 1, and now in this case we'll directly get 1 because it will directly subtract 7, which is here. So similarly for 8 it will be 3 and then 1 comma 1, which will be 4, and with 7 also you will have 2, and then for 9 it subtracts it will be 5, so it subtracted 5 and then 1 1 1 1, and for this case it subtracted 7 and then 1 and 1, so it will be 7 and 8 9 3, so here 10. So for this case what it will do, it will again subtract 5, so it will only be 2, so it will subtract 5 and it will go to 5 comma 5 and it will check, so here it's 1, so it will add 1 here. So this case will consider the minima, so it will be 2 again for this. Then for 11 it will take this and then it will go to 1 comma 1 and it will return 3, and this will return minima, which will be 3. So like this you can literally you can fill the table. This is exactly what a program is trying to do, so it slowly filled the whole table. Okay, now so till now we have used two-dimensional space I and j. Now we'll try to simplify it further by only using one-dimensional space. So let us see how do we do that. So I will change the table to single dimensional entity, then we are resizing it to only sum. We resizing it, and this time we will initialize it with -1. Then uh, simply it's passed. So now we'll see the changes. So in the previous case, the initialization was two rows you had to initialize, one row and one column you had to initialize. But since it's only a single row, so uh, now the initialization will simply be that if the sum is 0, you have to simply return 0. So that's all is the initialization part, right? So now this loop will remain the same. It will run from 1 till s. So this part you have to think how you are actually uh, you are calculating these, but you are not wasting space here. So we'll see how exactly that is being done. So uh, now we have to think about the further changes. So this particular loop is running across the second across V, and once again, if you have any doubt, you can please ask. 3 people are remaining.